Hello, my name is Hernando Burgos, a professor of mathematics. In previous video, I have explained what is probability. I explained also the basics concepts involved in the definition of probability. And I also explained ways to compute this probability. Today in this video, I will be explaining some rules that help us to compute probabilities. Sometimes we know the probability of some events and we need to know the probability of other events. For computing this probability, we need to know several rules. And the first rules are included in the definition of probability. If E is an event, then the probability needs to be a number between 0 and 1. So this is one rule. Also, the probability of the impossible event will be 0. So this number is for the impossible event, and this number will be for the certain event, for the sure event. So the probability of the certain event or the sure event, that is also the sample space, will be 1. So we know now this, that the probability of any event will be between 0 and 1, that the probability of the impossible will be 0, and the probability of the certain will be 1. Second, if E is an event, then no E is also an event, and the probability of no E equal 1 minus the probability of E. So this is very important in case that we know the probability of E, because immediately we can find the probability of no E. For example, a study was done of the 1,400 vehicles parked on the college parking lot last Friday. The results were as shown in the table. And I have two questions. What is the probability of finding a white car? And what is the probability that the car is not white? This is the table. So we have some cars. For example, there are some cars that are red, some are black, some are blue, etc. And we also have some SUVs, some sports, and some compact cars. In total, we have 400 cars. And they are asking me for the probability of a white car. I will be calling W, so I will be using this symbol for a white car. So let's compute it. So if we want to know this, and I know the number of cars, and I know also that there are 60 cars. If you notice here, this 20 means that there are 20 white cars that are SUV. And there are 15 cars that are sports, white cars. Yeah? So in total, there are 60 white cars. And if we want to compute the probability to be white, so I'm choosing one randomly, will be 60 over 400. So it will be very easy to compute it. 60 over 400, that is equal to 0.15 or 15% using your calculator. But the second question is, what is the probability that the car is not white? If they are asking me this question, then one idea will be counting all the cars that are not white. And that's just the number of cars that are not white divided by 400. Obviously, if we know this rule, it will be easy if we compute 1 minus the probability of white. So in this case, the event of interest is to be white. So this A is actually the W that we have in this problem. So probability of not white will be 1 minus the probability of white. So it will be easier to compute it in this way instead of counting all the cars that are not white. So in this case, we have 1 minus 0.15, that is 0.85 or 85%. And that answers question B in an easy way. So knowing this rule help me to solve some problems in an easier way. Okay, let's see another rule of probability. If A and B are mutually exclusive events, then the probability of A or B will be the probability of A plus the probability of B. And this is included in the definition of probability. So this is already a rule. And as an example of application of the rule will be this. Yeah? Remember that A and B are mutually exclusive if the probability of A and B equals 0. So it's impossible that A and B happen. Remember that the probability of the impossible is probably it will be 0. Yeah. So if it's impossible that A and B happen, we have that the probability of A and B is 0, or we say that they are mutually exclusive. So in this case, they are mutually exclusive. The probability of A or B will be the sum of their probabilities. As an example, we can see this. Yeah? A study was done of the 400 vehicles parked on the college parking lot last Friday. The results were as shown in the table. So this is the same table. But the question is, if we select randomly the vehicle, what is the probability that this vehicle is either blue or gray? So we can find the probability of being blue, then the probability of gray, because these two events are mutually exclusive. So a car cannot be at the same time blue and gray. So this is impossible that happen, these two events at the same time. So for that reason, I can use this formula. Yeah? The probability of A or B will be the probability of the first one plus the probability of the second one. And in this case, we compute the probability, so we're going to compute the probability of B or G. So we're probability of blue or gray. And this probability will be, because the formula says that it's the sum of the probability will be the probability of B plus the probability of G. But the probability of B blue is 76 over 400. Yeah? And the probability of gray will be 94 over 400. So what we need to do is just add together these two numbers, and this is the probability of B or G. So 76 plus 94, this is 170 divided by 400. And this is 0.425 or 42.5%. And this is the way to apply this third rule. Yes? So when we have two events that are mutually exclusive and we know the probability of each of them, then we can add together the two probability and we find the probability of the union, the B or G. So the probability of the first event or the second event. This is also the same that the probability that you are going to choose at least one of these two events. Let's see a fourth rule. For any events A and B, the probability of A or B, now any events, not necessarily mutually exclusive. If whatever two events A or B, the probability of A or B will be the probability of the first one plus the probability of the second one minus the probability of the two events happens at the same time, the probability of A and B. You can apply this rule for any two events. So not necessarily mutually exclusive or not mutually exclusive. So because if the events are mutually exclusive and you apply this rule, it will not be working well, because if the events are mutually exclusive, this will be 0. And the answer will be the third rules. So there is no problem if you are thinking in this rule all the time that you have A or B. Let's see an example. The same situation, but now we are going to compute this probability. If we select a vehicle, what is the probability that this vehicle is either compact or white? So these two events are not mutually exclusive because they can happen at the same time. I can choose a car that is at the same time compact and also white. Actually, there are 25 of these cars. These 25 cars are at the same time white and compact. So these two events are not mutually exclusive. So for that reason, I cannot use this formula. I need to use this formula. So in this case, we have this. If we want to compute the probability, I'm going to call compact with C. So we're going to compute the probability of being compact or white. And in this case, we have that this will be the probability of the first one, that the rules say, probability of the first one plus the probability of the second minus the probability of the two happening at the same time. So it will be the probability of compact plus the probability of W minus the probability of compact and W. Okay, and what is the probability of to be compact? There are existing here 22 plus 23 plus 42 plus 25. There are 128 cars that are compact. So this actually will be, the first one will be 128 divided by 400. So will be the probability of being compact. Plus the probability of being wide. Probability of being wide will be, actually there are 60 cars that are wide. So will be 60 over 400. So I'm going to type here plus 60 over 400 minus the probability of to be compact and wide at the same time. And there are 25 cars that are compact and wide at the same time. So for that reason, will be 25 over 400, this probability. So will be minus 25 over 400. It will be a good idea if you type this without simplification of this number, because if you do that, all the numbers have the same denominator. Then you will just solving the operation at the numerators, 128 plus 60 minus 25 and divided by 400. So it will be 163 at the top divided by 400. If you want to type this in decimals, will be 0.4075, and this is rounded to 4 decimal places. And this is 40.75% if you want to answer you want to give the answer in percentage. Let's see now another rule. For any events A and B, the probability of A and B equal the probability of A times the probability of B given A. And here appears another concept. This is the concept of conditional probability. So this is the probability of B given that A happened. Let's type here the definition of the conditional probability. The probability of B given A, and this vertical line will be read in this way. Probability of B given, so this line, I'm going to read this line as given A, denotes the conditional probability of B given A, and is the probability that the event B occur given that the event A already happened. So if there are two events and one of them already happened, then the probability of B may be changed. And this probability of B given that this A happened is called the conditional probability. Let's see an example to see it better. If we select a vehicle, what is the probability that this vehicle is compact and wide, for example? This is one thing that we can answer already. But this one, if we select a compact vehicle, what is the probability that this vehicle is wide? So now we are selecting a compact vehicle. So now the fact that the vehicle is compact already happened. So now here in the second question, I'm looking for the probability of the vehicle is wide, given that we know already that it's a compact vehicle. So in this case, we are finding the conditional probability. Let's find the first one, that is easy. What is the probability that this vehicle is compact and wide? So in this case, we are selecting a vehicle from all of these 400 vehicles. Yeah? So we are selecting one of them. And we are finding the probability of to being compact and wide. And in this case, what we have is the probability of C and W. So we need to find, on these 400 vehicles, what are at the same time compact and wide. And let's see, here are all the compact and here are all the wides. And I noticed that these 25 here are compact and wide. So we already answered this question, so it will be 25 over 400. And this is 0.0625, or if you can type 6.25%. But the second question is different. We know the vehicle is compact. So we went there and we looked for the compact vehicles, and we're going to find what is the probability that this compact vehicle, I'm going to choose one randomly, what is the probability that this vehicle is white. So I'm going to, in this case, what I'm finding is what is the probability that the vehicle is white, given that we know that it's compact. So this is different. Huh? And then in this case, we know that in this case we are analyzing only the compact vehicles. So we know that the vehicle is compact. So we know that this is one of these 128 vehicles. So I don't going to see the others. So if we want to compute this probability, will be good if I'm using as a whole sample space is 128, because I'm selecting one of these. So we know the vehicle is compact. I'm just going to select one of these 128. And from these 128 vehicles, there are 25 that are white. So because that already happened, I don't see any other part of this table. I'm just going to see this 128. And then the answer will be 25 over 128. And this is 0.1953. So I'm not using here this formula. I'm just computing the conditional probability. And for answer this question C and W, I didn't use the formula. Obviously, if I use it, the answer will be good. Yeah, so because now I know, for example, the conditional probability. So I can use this formula, but it's not necessary to use. There will be some times when it's necessary. For example, if I know the probability of A and we know the probability of B given A, so if we know the conditional probability, then I can find the probability of A and B. For example, now maybe it will be easy. But sometimes there are some times when we can compute this without a formula. For example, in this case, the probability, if I'm going to select one vehicle from this 400, what is the probability that this vehicle is white or is compact and white? Oh, there are 25 over 400. So the formula is not necessary. There will be cases when the formula is necessary. So I'm just going to show you now that the formula works, obviously. If, in this case, 19.53%, but if I'm selecting, if I am answering the first question, for example, again, and we want to find the probability that this vehicle is compact and white, and I want to use this formula just because I want to use it, then will be the probability of the first one, so the probability of being compact, times the probability of the second one given the first. So it will be the probability that the vehicle is compact times the probability that the vehicle is white given that is compact. And this is already done. Yes, it's 25 over 128. But the probability that the vehicle is compact is 128 over 400. Eh? So we have here 128 over 400 times 25 over 128. This 128 is cancelled. Yes, and then the answer is 25 over 400. That is the same answer that we obtain without the formula. Obviously, will be some cases, not when we have a table, because if we have a table like this, there is no necessity of a formula to compute this. But there will be other situations when we have information of the conditional probability and the information of the probability of one of the events, and we can compute easily the probability of the first event and the second event happens simultaneously. In this case is when it will be necessary to use a formula. Okay, there will be some situations, some important situations, things to know, that you don't need to think in this way because the two events are independent. If the two events are independent, then the probability of A and B will be just the product of the two probabilities without thinking in conditional. but we need to know what are independence. But it looks like we can define the independence event from this. Because I notice here that if this probability of B given A was the same of probability of B, these two formulas will be the same. Yeah? So it means that the two events are independent, and let's type it here. Two events A and B are independent if the probability of B is equal to the probability of B given A. So if A happens, does not change the probability of the other. We can think that the two events are independent if the occurrence of one of them does not influence the probability of occurrence of the others. Let's see an example using this table. We want to see if the events to be white and to be SUV are independent. So we want to see if in this table that is different to the previous one, there are 450 cars now, and we want to see if the event choosing a car that is white is independent to the event the car is compact. For doing that, it will be a good idea to see if one influence choosing one, if you choose one of these influence in the probability of choosing the other. And we are getting this in just one try. So I'm going to choose one car. When I'm choosing this car, the probability of getting a white car, because there are 60 cars and there are in this case 450 cars in total, the probability of being white, it will be 60 over 450, and this is equal 0.1333. This is the probability of being white. But what happens if I choose a car and I know that the car that I choose is a SUV? The fact that I choose a SUV is influencing the probability of the car is white. Let's compute it. Let's see. In car, we know that it's SUV. So now we know that there are in total 150 of them. In total, there are 150. But from these 150, 20 are white. So this probability will be choosing a car that is white, given that we know that it's a SUV, will be 20 over 150. So 20 over 150. And this is equal to 0.1333, the same number. So the fact that the car is SUV doesn't change the probability of being white. In this case, okay, in this example. So in this example, we're gonna see, or in this parking lot, we're gonna see, we're going to say that these two events are independent, because if one of them happens, doesn't change the probability of the other. So in this case, the events W and SUV are independent because the probability of W is the same of the probability of W given SUV. Maybe sports and white are not independent. Yeah? Maybe in this case, or maybe a compact and gray are not independent. We should check. So sometimes people use this as a definition of independent events. The occurrence of one of them does not influence the probability of occurrence of the others. But to be true, a good definition will be this one that is here. The probability of B is the same of the probability of B given A, because this is something that you can check. So just compute the probability. If the fact that one of them happened change the probability of the other, oh, okay, so in this case they are not independent. In this case, they are the same, so they are independent. Are the events to be white and to be SUV independent? And we notice that they are not independent. But another way to see that is just using this, yeah? The probability of A and B equal the probability of A times the probability of B. So sometimes people use this as definition independent event. Let's see that. Let's compute the probability of W, and then the probability of W will be probability of being Y will be 60 over 450 times the probability of SUV. The probability of being SUV will be 150 over 450. And if you compute this in your calculator, the answer is 0.0444. What happens if you compute the probability of A and B? In just one, without a formula. If we know that, then the probability of A and B, W and SUV, will be, oh, these are the 20 cars that are at the same time white and SUV. So it will be 20 over 450. It will be 20 over 450. And if you do that, you notice that the answer is the same. Because these two numbers are the same, then we say that these two events are independent. Okay? So we can use this as a definition of independent. But there will be some situation when we consider that the two events are independent, and then we use this formula to compute the probability of A and B. But as I told you, it's not necessary in most of the cases. Most of the cases, this is easy to do, and in most of the cases, what we do in real life is use this definition to notice if the two events are independent or not. Let's continue with the initial problem that we have related to the vehicles in the parking lot. If we choose a blue vehicle, what is the probability that this vehicle is a sport? Are the events being blue and being sport independent? Let's see, this is the initial table. And there are in total 76 vehicles, vehicles that are blue. And there is also a sports vehicle, there are 122. We know that A and B are independent if the probability of A given B is the same of the probability of A. So we know this is the definition of independent events. Okay, let's answer question A. If we choose a blue vehicle, what is the probability that this vehicle is a sport? So we already know that the vehicle is blue. So we are choosing a blue vehicle. So we are finding the probability of being a sport given that the vehicle is blue. So that is given. And so we know that there are in total 76 blue. And from this 76 blue, there are 24 that are sport. So if we know that the vehicle is blue, so we don't need to see any other part of the table, just this part. So our whole universe is this. And from this 76, we are choosing 24. So the answer will be 24 out of 76. And this is 0.3158 or equal to 31.58%. Now we need to check what is the probability that the vehicle is a sport. And we need to check if the probability of being a sport is the same of the probability of the vehicle being a sport given that it's blue. So we want to know if the fact that it's blue changes the probability of being a sport. So the probability of S given blue, we know that is the number that we get, 31.58%. The probability of being a sport is equal to 122 divided by 400. And this is 0.35 or 30.5%. So comparing these two numbers, we've noted that these are different. Since the probability of being a sport given that the vehicle is blue is different than the probability of being a sport, we conclude that the B and S are not independent. Let's see now another example of application of this rule of probabilities, different from these tables. A construction company has submitted two bids, one to build a large soccer stadium and the other to build a large shopping complex. The company believes that it has 20% chance of winning the stadium bid. and 60% of winning the shopping complex bid. The company is sure that these two events are independent. So they are sure of this. So that we are going to use that the fact that they are independent as an assumption, and we are going to be using the formula for independent event. Okay, let's see what question we have. What is the probability that the company does not win the stadium contract? So it will be the idea to compute the probability of getting the stadium contract. And we have this. So we know there are several information here. For example, the company believes that it has a 20% chance of winning the stadium bid. So there is a 20% chance of winning the stadium win. We are going to consider this. This is a subjective probability, but we are going to consider as a probability. So there will be the probability of winning the stadium bid, and I'm going to call this PS 0.20. The other is winning the bid of the shopping complex. Let's call it PC for complex, and then probability of C will be 60%. This is another information, and with that we need to compute what is the probability that the company does not win the stadium. So we are going to computing the probability of no is. So will be the probability of no is, because we know the probability of S, so will be 1 minus PS. And this will be 1 minus 0.20 equal 80%. So knowing the probability of some events help me to understand the probability of other events. Let's analyze a second question. What is the probability that the company win both contracts? And this is, we remember, win both contracts. We have two events. And the probability that the two events happen is the probability that the first happen and the second happens. So will be the probability of P of S and C. And now I'm going to use the fact that that these two events are independent. So because if the two events are independent, the probability of S and C will be the product. So it will be the probability of S times the probability of C. And we know this is 0.20 and this is 0.60. So it will be 0.20 times 0.60, and this is 12%, 0.12 or 12%. Okay, good. There's another question. What is the probability that the company win at least one of these contracts? When I say at least one, they are telling me the probability that win the first or the second. Yeah? So will be the probability of S or C. Will be probability of S or C. So we need to understand that when I say both contracts, it refers to the probability of the first and the second. When they say at least one, it means the probability of the first or the second. And the formula for probability of S or C will be the probability of S plus the probability of the second one minus the probability of the interception, the probability of S and C. And we have all this information. We have probability of S they give us. We know the probability of C, and we have computed the probability of S and C. So in this case will be 0.20 plus 0.60 minus 0.12. That was the number that we computed at the beginning. And then we obtain 0.80, 0.68, yes, 0.68 or 68%. And in this way, we solve problems related to probability. With this, I conclude the explanation of these probability rules.